So in the last class, we discussed Rutherford's gold foil experiment, right? Rutherford's gold foil experiment gave us the first insight into the structure of an atom. Rutherford told us that all the positive charge and almost all the mass of the atom was concentrated in a very small space inside the atom, and this space he decided to call nucleus, right? All the mass and almost all the mass and all the positive charge is concentrated in this space, right? And this he proved through his gold foil experiment. We saw the various observations and the inferences drawn from there. But we discussed two drawbacks of Rutherford's model. First, he could not explain the stability of the atom. He could not explain why the electrons were not falling inside, right? Why the electrons were not going inside the nucleus, Rutherford could not explain. And the second, he could not explain the hydrogen spectrum, right? We left this discussion over there, and then we went on to study about the electrostatic force field a little bit. We understood Coulomb's law, kq1 q2 by r square, the force of attraction between two charged particles. We understood photoelectric effect, right, which was discovered by Einstein. We learned how to do those calculations also, right? Then we came to Bohr's model of the atom, and we were there. Bohr's atomic model. And what did Bohr tell us? Bohr told us that the electrons can exist only in discrete orbits around the nucleus. मतलब कहीं पे भी नहीं रह सकता, या तो इधर होगा या इधर होगा या इधर होगा. He gave us that the electron can only exist in discrete orbits around the nucleus. So obviously he had to give us the location of this orbit. The location of this orbit, he said, is such that the angular momentum of the electron will be an integer multiple of h upon 2 pi, right? The angular momentum is given by mvr, this we saw, and it is an integer multiple of h upon 2 pi. It has to be so, right? So we got two equations there. The first equation which we wrote over there was the force balancing equation. The electrostatic force of attraction between the nucleus and the electron, that is balanced by the centrifugal force. The centrifugal force, I gave you the simple formula for that as mv square by r. The derivation of this formula is later on in physics, right? So the first equation which we had was kz e square by r square is equal to mv square by r. We also understood why this potential energy was negative, right? We also understood that our reference point is infinity, right? The potential energy of this electron at a distance r from the nucleus was defined as the work done in bringing the electron from infinity to a distance r, right? And because this work was in the direction of the force field, this work done was negative. Whenever we move an object opposite to the direction of the force field, its potential energy increases. But if we move it in the direction of the force, its potential energy decreases. And we use the of integration to calculate this potential energy, and I told you that that definite integration you will study later in class 12, so you don't need to worry about that, but this result you have to remember. So the total energy comes to minus kz e square by 2r, also minus 13.6 into z square upon n square electron volts. Very important formula. This is the energy of an electron in orbit n. You can put it in the orbit number, you will get the energy. So यहाँ तक हम पढ़े थे. And then we also understood that when electrons absorb energy, they move to higher orbits, and when they jump from higher orbits to lower orbits, they release energy. And this energy is always released in the form of photons, which we can see, right? And that's how I discussed how these tube lights are working. We understood that. Yes or no, right? What is happening here are electronic transitions. The electrical energy is sending the electrons to the higher energy state, and then when these electrons are jumping back to the ground state, what are they doing? They are releasing photons, and these photons we can see. Yes or no? यहाँ तक हम पढ़े थे last class. Okay. Now, if you open class assignment 2, and I want you to simply solve question 1. Calculate the velocity of an electron in the third orbit of helium plus atom. Also calculate the total energy of this electron. We'll directly put in our formula for velocity, right? But in our formula for velocity, what is n therefore now? Where is the electron? Third orbit, so n is equal to 3. And because the atom is helium plus, what is z? Z is 2, right? Z is the atomic number. So because the atom given to you is helium plus, Z is 2. So velocity will be 2.18 into 10 power 6 into Z by n, so into 2 by 3 meters per second. I think this comes to 1.5 into 10 power 6 meters per second. Straightforward. You just have to apply the formula. You must remember these formula. Next, we also have a formula for radius, right? 0.529. Acha, radius we don't have to calculate. What is the question asked for? Energy. Energy. So the energy of the electron in helium plus atom in orbit number 3 will be minus 13.6 into z square by n square. So 2 square by 3 square electron volts. How much does this come to? आई होप तुम लोग कैलकुलेटर लेके आए हो. कैलकुलेटर लगेगा आज के क्लास में. फोन पे नहीं यार, साइंटिफिक कैलकुलेटर यूज करो. फोन पे बहुत ही, अच्छा फोन पे भी है तो कर लो, बट how much minus 6.04 इलेक्ट्रॉन वोल्ट्स. ठीक है, direct application of formula, nothing hanky panky here. Okay, next question. Calculate the ratio of energy of two electrons. One is in the first excited state of lithium plus 2 and the other is in the second excited state of helium plus. Now these terms you must understand well. For example, if an electron is in n equal to 1, if it is in the first orbit, then we say that the electron is in the ground state. This is the lowest energy state. See, anything in this world wants to do what? Reduce potential energy. If I take this pen and I leave it, what will this pen do? It will fall down, no? It will not go up. Why is it falling down? Because when it falls down, what does it do? It reduces potential energy, right? So that's what the electron also wants to do. So the electron always wants to come to the ground state, to the lowest energy state, right? Which is orbit number 1, right? So if electron is in n equal to 1, we say that the electron is in the ground state. If the electron is in n equal to 2, this is known as the first excited state. Dhyan dena. First excited state is not the first orbit. The first excited state is the second orbit. N equal to 3, therefore, is the second excited state, and so on. N equal to 3 is the second excited state, right? Now solve. Solve question number 2 now. 81:16, yes. Where are the electrons? One is in the first excited of lithium plus 2. So the first electron is in lithium plus 2 and the first excited state means n equal to 2. And the second electron is in helium plus and second excited state. The other electron is in helium plus and second excited state means n equal to 3. So this ratio I have to calculate. So what will this be? This will be minus 13.6 into z square by n square. Lithium atomic number is 3. So 3 square by 2 square upon minus 13.6 into 2 square by 3 square, z square by n square, right? So minus 13.6 all cancels. So 9 into 9, 81, 4 into 4, 16. 81 by 16. I will describe to you why Rutherford could not explain the hydrogen spectrum and how Bohr's model does that. First of all, what is the spectrum, right? We've discussed the electromagnetic spectrum, right? We have the visible range between 3800 to 7600 Armstrongs, right? Wavelengths lesser than 3800 ultraviolet. Then below that we have and below that we have gamma rays. More than 7600 Armstrongs is infrared radiation. Then more than that is microwave, and then we have radio waves, etc. So when light could be made up of many types of electromagnetic waves, right? When, like for example, this light which is falling on us is made up of many types of photons, right? This is visible light. It has violet also, it has indigo also, it is red also, right? If I allow light to pass through a prism, you must have done this experiment as children. If you allow electromagnetic waves made up of many different types of wavelengths and many different types of photons, if you let it pass through a prism, what happens? This light splits, and what I can do is, if I place a photographic plate over here, I can record my observation. What will you notice on this plate? You will notice bands. Right? You'll notice equally spaced bands of this. This is just the visible spectrum, but even the ultraviolet photons, even the infrared photons, they also split. But this we can see. We can see VIPG, YOR, right? What we see here is all the colors, and these colors are merging with each other, right? And this is what we call the continuous spectrum. This is what is called the continuous spectrum. All the photons are available, right? From 3800 to 7600, all the photons you can see. Now, what happened? Something strange happened here. This light, before I let it enter the prism, I allowed this light to pass through some cold hydrogen gas. I allowed this light to pass through some cold hydrogen gas before I let it fall into the prism. I observed this. I got my spectrum, but in the spectrum were certain dark lines. This spectrum had certain dark lines, right? Which meant what? See, this line or this violet region is 3800 Armstrongs. Then there's 3800.5, 3801. I'm not saying 0.5 yoga, but they are all the photons are available. But this dark light indicates what? This dark line over here indicates that a certain photon is missing. This dark line on the spectrum indicates that a certain photon is missing from the spectrum, which means the hydrogen gas must have absorbed that photon, because when the hydrogen gas was not there, we got a continuous spectrum. We got all our photons, but when we passed it through hydrogen gas, certain photons went missing. Certain photons went missing. Now, if I look at the energy of hydrogen gas, the energy of the first orbit is minus 13.6 electron volts. The second orbit is how much? Minus 3.4 electron volts. The third orbit is minus 1.51 electron volts. The fourth orbit is minus 0.8 electron volts, etc. It keeps going on. It keeps going on. Now, pay attention, please. If my electron is here in orbit number 1, in the ground state, the difference between these two orbits is how much? 10.2 electron volts. The difference between here and here is 1.9 electron volts. The difference between here and here, between 1 and 3, is 12.1 electron volts, and so on, and so on. My point is, if I give this electron 10.2 electron volts of energy, this electron will jump from orbit 1 to orbit 2. If I give this electron 12.1 amount of energy, what will this electron do? It will jump from orbit 1 to orbit 3. But suppose I give this electron 5 electron volts of energy, right? Suppose I gave it energy 5. अगर 10 तक में यहाँ पहुँचता है तो 5 तक में कहीं यहाँ बीच में पहुँचना होगा. But what is not possible? The electron cannot be in between. That's what Bohr is saying, that the electron can only exist in discrete orbits. It will either be here, that means the electron will either have energy this much, or have energy this much, or have energy this much. The electron cannot possess energy apart from these values, right? So if I give this electron a photon which has 5 electron volts of energy, that would want to take the electron somewhere here, but is that position possible? No. So the electron won't absorb that photon, because that photon cannot take it to a allowed orbit. It is taking it somewhere in between. That photon the electron cannot absorb only. Which photons can the electron absorb? The electron can only absorb those photons which can take it to a higher orbit, right? And those higher orbits are fixed. मतलब इलेक्ट्रॉन या तो 10.2 इलेक्ट्रॉन वोल्ट्स वाला फोटोन अब्सॉर्ब करेगा, या 12.1 का अब्सॉर्ब करेगा, या अगर यहाँ पे है ऑलरेडी तो 1.9 का अब्सॉर्ब करेगा, right? But if you give it a photon of 5 or 6 or 7 electron volts, will it absorb those photons? No, because those photons cannot take it to a higher orbit. So that is what has happened, right? Those photons which could not take the electron to a higher orbit have been unaffected. They have passed through the gas and we can still see them. We can still see them. But there are certain photons which are missing. These missing photons must have how much energy? These missing photons must have energy equal to the difference in energy between the orbits. Yes or no? Which photons will be missing from here? वो photon जिसका energy 10.2 electron volt होगा वो missing होगा. वो photon जिसका energy 12.1 होगा वो missing होगा. The photon which has energy 1.9, that will be missing. Yes or no? Which is the photon which has energy 1.9 electron volts? देखो, energy का I gave you a shortcut formula 12400 by lambda, right? So if the energy is 1.9 electron volts, then 12400 by lambda, this lambda comes to around 6500 Armstrongs. This is like an orange colored photon somewhere here, right? What do we notice? It is missing. This photon is missing. Yes or no? Right? Isn't this interesting? The photons which are missing from my spectrum are those photons which could take the electron to a higher orbit. And so which photons are those? It is those photons whose energy is equal to the energy difference between my orbits. Please make sure you understand this well. This is what we call a discontinuous spectrum. This is a discontinuous spectrum because not all the photons are present, right? Some photons are missing, and this is called the absorption spectrum of hydrogen. In this colored band, you notice there are black lines. Can all of you see this? Right. There are some lines in violet over here, so one line in blue over here, one orangish line, right? Right. I hope you can see this. Right. Some lines are missing from my spectrum. Lines are missing. Yes. So those photons which correspond to energy differences in the atom, those photons have been absorbed. Right. Now this thing Rutherford could not explain. This experiment was performed before Bohr had proposed his model. So that's why it became a drawback for Rutherford's model, because Rutherford could not explain why certain photons are getting absorbed by hydrogen and others are not getting absorbed. Yes. Another part of this experiment was this, that instead of taking cold hydrogen gas, what I did was, let's say I have a tube here which is filled with hydrogen gas, and I pass electricity through this. I pass electricity through this tube. What will happen? The electrical energy will be absorbed by the electrons present in the hydrogen atoms. The electron will absorb the electrical energy, and what will it do? It will jump to higher orbit. It will jump to higher orbit, but the electron obviously is not happy in the higher orbit. What will it do then? It will jump back to the ground state. It will jump back to the lower orbits, right? And in the process of jumping back, what will it do? It will emit light. It will emit light, it will emit photons. This light which is emitted is passed through a prism. This light which is emitted is passed through a prism and analyzed. And then on a photographic plate, what will you see? Can you tell me what will you see on the photographic plate? I repeat my question. Electricity is passed through. The electrons go to higher orbit. Now the electrons are jumping from higher orbits to lower orbits. In the process, they are emitting photons. Those photons are passed through a prism and analyzed. What will you see? Exactly. Exactly. The lines which were missing are the only lines you will see now. The spectrum is going to be completely black, and it will have one colored line here, one colored line here, one colored line here. That is all you will see. Because if it requires 1.9 electron volt to take the electron from 2 to 3, when the electron jumps from 3 to 2, it will emit the same amount of energy. तो जो फोटोन उसको 2 से 3 ले जाने में absorb हुआ था, जब वो 3 से 2 आएगा तो वही फोटोन को emit करेगा. Yes or no? Right? So the lines which were missing from the absorption spectrum are the exact same lines which will be visible in the emission spectrum. This is known as the emission spectrum of hydrogen. This is the emission spectrum of hydrogen, and this is what it looks like. Dekho. Can you see here? The top spectrum, the top spectrum is the emission spectrum. What do you see? It's completely dark, but you only see certain colored lines, right? And below we have the absorption spectrum. It is colorful. It has almost all the photons except for some. Are you getting it? Right? So this spectrum could be explained by by Bohr's model. Rutherford could not explain this spectrum, but Bohr can explain this spectrum. Any doubts? ठीक है? the lines which we see in our electromagnetic spectrum have energy corresponding to energy differences between the orbits. That's the idea. Please attempt question 3. Calculate the frequency of an electron in the third orbit of helium plus hoga. वो helium नहीं होगा. Make a small correction. Question 3, it will be helium plus. Now, first of all, what is frequency? Let's understand that. I first define a value called time period, capital T, right? Time period is the time required by an electron to complete one revolution around the nucleus, right? Simple. The electron is moving around the nucleus. Yes, it has certain velocity v, which we know how to calculate. So what will be the time required to complete one revolution? Time is distance by speed. Yes. So what distance is the electron covering in one revolution? How much distance is the electron covering in one revolution? 2 pi r. If you know the formula for radius, it is covering the circumference, yes or no? So distance covered by the electron is 2 pi r, and the velocity of the electron is v. So the time period of revolution is 2 pi r by v. Yes or no? Now, what is r proportional to? R is proportional to n square by z. So the numerator will have n square by z. And what is velocity proportional to? Z by n. The other values are constant. So what is it proportional to? Z by n. So the denominator will have z by n. So this becomes proportional to n cube by z square. Right? So an important result is this, that the time period is proportional to n cube by z square. You can use this result for many numericals, right? Many numericals you can solve with this shortcut. You know, you could get a numerical that this is one electron in this atom, this is another electron in this atom. Calculate the ratio of their time periods. So you don't have to do the complete calculation, right? You can simply use this relationship. Acha. The inverse of time period, 1 by time period, is what? Frequency. What will this frequency tell us? This is not the frequency of an electromagnetic wave. What will this frequency tell us? This frequency will tell us the number of revolutions made by an electron in 1 second. Right? It will be this frequency. Yes or no? So what will this be? Velocity upon 2 pi r. And what will frequency then be proportional to? Z square by n cube. Frequency will be proportional to z square by n cube. Right? What is this frequency? This frequency is the number of revolutions the electron makes in 1 second. The number of revolutions the electron makes in 1 second around the nucleus. So calculate this value. Calculate the frequency of an electron in the third orbit of helium plus atom. Please do this for me. Z equal to 2, orbit is 3. Calculate the frequency of this electron. Please put in the values v upon 2 pi r. Please solve this. Calculate the frequency of an electron in the third orbit of helium plus. Okay, so the velocity is 2.18 into 10 power 6 into z by n, means 2 by 3 upon, now this is in meters per second. This is in meters per second. So the denominator, if that is in meters, then the frequency obviously we'll get in hertz. So this will be 2 into pi into radius will be 0.529 into n square by z third orbit. So 3 square by 2 into 10 power minus 10. This is in meters now, right? If you solve this, 1.45 into 10 power 15. I am getting this, but anyway, you can check this again at home. What do you observe from here? What do you observe from here? ये value देख के तुमको क्या पता चलता? Can you feel this value? What does this value mean? The frequency is the number of revolutions the electron makes around the nucleus in 1 second, right? It's revolutions per second. That's hertz, right? How much is it? 1.45 into 10 power 15. Can you imagine how fast the electron is moving then? The electron is making 10 power 15 revolutions around the nucleus in 1 second. Isn't that incredibly fast? Yes. So when you imagine the motion of an electron, around the nucleus, don't imagine it to be moving like this. The electron is moving very, very fast. It's like if this fan was moving really fast, would you be able to see the individual blades? No. What would you see instead? You would see a cloud, right? That's what we should imagine the electron also as. You cannot see the particle moving around the nucleus very fast. What you see is a cloud of negative charge. That's what we really end up seeing. Yes or no? So this is just for visualization. Anyway, next. Next. Also calculate its ionization energy and binding energy. Write down the definition, please. The energy required to remove an electron from the ground state to infinity. The energy required to remove an electron from the ground state to infinity is the ionization energy. The energy required to remove an electron from the ground state to infinity is the ionization energy. So tell me, the electron is right now in the first orbit, and where do I have to take it? Infinity. In general, if I have to take an electron from, let's say, n1 to n2, I will generally use n1 for the lower orbit and n2 for the higher orbit. The energy required will be how much? The difference in energy between these two orbits. So the energy required, delta E, let me call it, will be energy of n2 minus energy of n1. Right? This will be the energy required to move an electron from n1 to n2. This much energy I will require. So if I want to move it from the first orbit to infinity, so how much is ionization energy then? Ionization energy is E infinity minus E1. Right? If I want to move the electron from 1 to infinity, then the ionization energy is E infinity minus E1. How much is E infinity? 0. If I put n equal to infinity, that is 0. The energy of the electron at infinity is 0. Minus 13.6 into z square upon 1 square. So the ionization energy becomes 13.6 into z square electron volts. Important formula. The ionization energy of an electron is 13.6 into z square electron volts. Okay. And write down another definition: binding energy. Binding energy. The energy required to move an electron, the energy required to move an electron from its current orbit to infinity. The energy required to move an electron from its current orbit to infinity is binding energy. The energy required to move an electron from its current orbit to infinity is binding energy. So please solve the next two parts of question 3. Calculate the ionization energy and the binding energy of an electron which is in the third orbit of helium plus. Electron is in third orbit of helium plus. For this electron, please calculate the binding energy and the ionization energy. Right. How much did you calculate the ionization energy as? Yes. Ionization energy will come to 54.4 volts. Electron volts, ionization energy, so electron volts. And binding energy kitna aaya? 6.04 electron volts. Good. Write down another definition, that is ionization potential. Write down another definition, ionization potential. The potential required to give an electron, the potential required to give an electron at rest a kinetic energy equal to the ionization energy. The potential required to give an electron at rest a kinetic energy equal to the ionization energy is ionization potential. Is ionization potential. So what I'm saying is that the ionization energy is how much over here? 54.4 electron volts, right? So if I have an electron at rest, right, and I put it in an electric field, how much should be the potential of this battery so that by the time the electron comes here, its kinetic energy is 54.4 electron volts. What should be the potential of this battery? 54.4 volts, right? So whenever you see the term ionization energy and ionization potential, they are many times used interchangeably. If the ionization energy is 54.4 electron volts, then the ionization potential is 54.4 volts. Numerically the same value, just the unit is different. अगर energy बोल रहा है तो electron volts होगा, और अगर potential बोल रहा है तो volts होगा. That's all. Clear? All right. Now next, question number 4. Calculate the third excitation energy for lithium plus 2. Let's understand what this means. Minus नहीं हो सकता ये. I'll explain why. Calculate the third excitation energy for lithium plus 2. Now, you have calculated the energy of the orbit perhaps. Let's understand what it means. The first excitation energy is the energy required to move the electron from orbit 1 to orbit 2. Electron को 1 से 2 भेजने के लिए जितना energy चाहिए, that is called the first excitation energy. So first excitation is from n1 equal to 1 to n2 equal to 2. This is the first excitation. The second excitation is what? The second excitation is from n1 equal to 1 to n2 equal to 3. Please ध्यान रखना ये. There's a technical term. The first excitation is from 1 to 2. The second excitation is from 1 to 3. It's not from 2 to 3. It's not from 2 to 3. This point you have to remember. So in the same way, the third excitation will correspond to what transition? 1 to 4. 1 to 4. Yes? So if the question is asking you for the third excitation energy for lithium plus 2, the energy required in lithium plus 2 to take the electron from 1 to 4. The energy required in lithium plus 2 to take the electron from 1 to 4, this will be how much? E4 minus E1. E4 minus E1? Please solve. Tell me how much is this coming to? Minus 13.6 into z square means 3 square by n square, z square by n square. Minus 13.6 into 3 square by n square. ये होगा ना? Please solve. Tell me how much is this? Yes. This will come to 114.75 electron volts. This is the energy required to move an electron from the first orbit to the fourth orbit in lithium plus 2. So this is the third excitation energy of lithium plus 2. Also calculate the ionization energy for lithium plus 2. Tell me, what will be the ionization energy for lithium plus 2? Yes, the ionization energy comes to 122.4 electron volts. Right? You directly apply the formula 13.6 into z square. So 13.6 into 3 square. That's all you have to do. 13.6 into 9, it comes to this. This value would obviously be more than the excitation energy. Yes or no? 1 से 4 ले जाने के लिए जितना एनर्जी चाहिए, 1 से पूरा इंफिनिटी तक ले जाने के लिए उससे ज्यादा एनर्जी लगेगा. So if it requires 114.75, then the ionization has to be more than that. Yes. The question says that the first excitation is 40.8 volts, which means the first excitation energy will be how much? 40.8 electron volts. If the first excitation potential is 40.8 volts, the first excitation energy will be 40.8 electron volts. Yes, Z equal to 2. The first excitation energy means energy required to take the electron from 1 to 2. This will be E2 minus E1, energy of electron in second orbit minus energy of electron in first orbit. This is given as minus 13.6 into z square by 2 square minus 13.6 into z square by 1 square, and this is given as 40.8. So all you have to do is solve for z. You will get z square equal to 4. So z equal to 2. If z is equal to 2, therefore the atom is what? The atom is helium plus. Right? If Z equal to 2 is what we get, then the atom is helium plus. So this is the first part. Yes. Next 5b बताओ. What is the second excitation potential? माइनस कैसे हो सकता है यार? केमिस्ट्री में हमेशा याद रखना, अगर एनर्जी तुमको देना पड़ रहा है तो वो एनर्जी हमेशा पॉजिटिव होगा, एंड अगर एनर्जी कहीं रिलीज होता है वो एनर्जी नेगेटिव होता है. ऑलराइट, energy required to take the electron from 1 to 3, this will be E3 minus E1, so minus 13.6. Now Z we know, so 2 square by 3 square minus 13.6 into 2 square by 1 square. This I think will come to 48.3 electron volts. This will come to 48.3 electron volts. And what is the third part? What is the ionization energy? Ionization energy we've already calculated before. It is 54.4 electron volts. Obviously the ionization energy is going to be more. 1 to 2 requires 40.8 electron volts. So 1 to 3 will obviously be more than that. It's 48.3. And 1 to infinity will obviously be more than that. It is how much? 54.4. Now let's think about the reverse. Let's think about the reverse. An electron is jumping from higher orbit to lower orbit, right? The electron is jumping from N2 to N1. This transition is happening. From higher orbit, the electron is jumping to the lower orbit, N1. We always use N2 for the higher orbit, we always use N1 for the lower orbit. That's a convention. In this process, what will happen? Energy will be released, right? How much energy will be released? If I want to know the magnitude of the energy released, it will be energy of N2 minus energy of N1. Yes, because N2 is higher energy, right? So higher minus lower, this will be the positive value. So the energy released is En2 minus En1. But how is this energy released? It is released in the form of a photon. And what is the energy of a photon? H nu. Or we can also write it as hc by lambda. So delta E is the amount of energy released, and it is in the form of a photon. So can I not write this as hc by lambda? Yes or no? I can write this as hc by lambda. Yes, so if I put it over here, I will get hc by lambda as minus 13.6 into z square upon n2 square minus 13.6 into z square upon n1 square. I will get this. Or I can rearrange the terms to get 1 by lambda is equal to 13.6 upon hc into z square 1 by n1 square minus 1 by n2 square. I can get this. Now, this value which we have here, 13.6 upon hc, this is a constant, is it not? 13.6 is fixed, h is fixed, c is fixed. So if I plug in the values here, this is known as r, which is Rydberg's constant. And this value is 1.097 into 10 to the power 7 meter inverse. 1.097 into 10 power 7 meter inverse. This is R, which is also called Rydberg's constant. Is it okay? So we have a very neat formula that 1 by lambda is R z square 1 by n1 square minus 1 by n2 square. Very, very important. You will get numericals on this formula in every exam. Whatever first term unit test, whatever happens in school, you will get definitely a question on this formula. Right? When an electron jumps from n2 to n1, it will emit a photon. We can calculate the wavelength of that photon using this formula. Lambda is the wavelength of the photon emitted. R is Rydberg's constant, whose value we know. Z is the atomic number, and the electron is jumping from n2 to n1. This we know. Right? 1 by lambda is also written as V dash or nu dash, right? This is known as the wave number. The wave number will, what will be the unit? Meter inverse or centimeter inverse, right? It is 1 by wavelength. The wave number is essentially 1 by wavelength. So it's measured in meter inverse or meter inverse. Now obviously, if you put in the value of r and z and the orbits, you will get 1 by lambda. So if wavelength is being asked, अगर wave number पूछ रहे तब तो ये formula use करेंगे. But अगर wavelength पूछ रहे, then what will happen is you will have to take the reciprocal of whatever answer you get. You have to take the reciprocal of that. So that becomes a little time consuming in an exam. So what do I recommend? you can also remember the formula for lambda only. Lambda will be what? 1 by r upon z square, 1 by n1 square minus 1 by n2 square. This will be the direct formula for lambda, and r ka value we know. So what I have done is I have made this simple for you. I have calculated this in Armstrongs. I will give you a shortcut. This shortcut you have to remember. Lambda is 912 912 upon z square 1 by n1 square minus 1 by n2 square. You will remember this shortcut. Lambda is 912 upon z square 1 by n1 square minus 1 by n2 square, and this will give you the wavelength of the emitted photon directly in Armstrongs. This will give you the wavelength of the emitted photon directly, and in what unit? Armstrongs. I have done the math for you, but do not use this in school. Okay? In school they will not recognize this formula. In school and boards they will recognize this formula. Is it okay? So that is a shortcut for exams. This is what you have to use in school. So tell me then, what will be the wavelength of the photon emitted when an electron in the hydrogen atom jumps from the second orbit to the first orbit? Please apply the formula and tell it to me. Calculator leke baitho. Tell me the wavelength of the photon emitted when an electron jumps from the second orbit to the first orbit in hydrogen atom. Solve. Use this shortcut. If it is hydrogen atom, then Z is 1. It is jumping from 2 to 1, so N1 is 1 and N2 is 2. So 1 by 1 square minus 1 by 2 square, so 1 minus 1 by 4, 3 by 4 हो गया ये. ऐसे करके solve करो. Please solve. Please solve. Yes, 1216 Armstrongs. ठीक है? So when an electron jumps from second orbit to first orbit in hydrogen atom, it will emit a photon whose wavelength is 1216 Armstrong. Tell me then for 3 to 1. If the electron jumps from 3 to 1, what will be the photon emitted? Please solve. 1026. Okay. 1026 Armstrongs. Next, tell me, if it is jumping from 4 to 1, what is the wavelength of the photon emitted? 97. Okay. 972 Armstrongs approximately. Right. And finally, now tell me this. What if the electron is jumping from infinity? What if the electron is jumping from infinity to the first orbit? Yes. Then the wavelength will be 912. Yes or no? Right? So, where do these photons lie? In your electromagnetic spectrum, violet light was 3800 Armstrongs and red light was 7600 Armstrongs. So 1216, 1026, 972, 912, ये सब कहाँ lie कर रहे हैं? In the ultraviolet region. These wavelengths lie in the ultraviolet region. So when an electron jumps from a higher orbit to the first orbit of hydrogen atom, it releases photons which lie in the ultraviolet region. So we write here that for hydrogen atom, N1 equal to 1 and N2 could be 2, 3, 4 and it can go up till infinity. The electron is jumping from a higher orbit to the first orbit and it releases a series of photons, right? These are known as the Lyman series. Lyman. This is known as the Lyman series and they lie in the UV region, right? These are known as the lines of the Lyman series and they lie in the ultraviolet region for hydrogen atom. For hydrogen, they lie in the ultraviolet region. Are you getting it? Right, very interesting. N1 equal to 1, N2 could be 2. This jump, which is from infinity to 1, right? From infinity, if the electron jumps to N1, this is known as the series limit. This is known as the series limit. From infinity to N1, that is known as the series limit. Calculate this then. Calculate this photon. An electron is jumping from the third orbit to the second orbit in hydrogen atom, and it is releasing a photon. Calculate the wavelength of this photon. Use the shortcut. हाइड्रोजन एटम है तो z equal to 1, but electron 3 से 2 jump करके आ रहा है. How much is coming? 6566. Yes. 6566 Armstrongs. Now where does this photon lie? Visible range. Right? Now when the electron is jumping from 3 to 2, it is emitting photons in the visible range of the spectrum. What about this? Tell me, 4 to 2. Solve, फटाफट. 4 to 2. Tell me. 4864 Armstrongs. Again, where does this lie? Visible region again, right? So this is a visible photon, right? So tell me the series limit. Tell me the series limit from infinity if it is jumping to 2. What is the series limit? How much is the series limit? 3648. Right? This is 3648. Where does this lie? It is just less than 3800. Huh? It is just less than violet. The wavelength is just, so which region is it? Ultraviolet. So most of the photons are in the visible region, but there are some photons in the ultraviolet region also. And this is a mistake in many books. This series is known as the Balmer series. And it has photons in the visible, which is main, plus it could also have photons in the ultraviolet region. Right? Visible and ultraviolet. The series limit is in ultraviolet. Now, please note, the question could be framed in many different ways in this topic. Okay. This transition from 2 to 1, this is known as the first line in the Lyman series. Right? So if someone tells you what is the wavelength of the photon emitted when, or what is the wavelength of the first line of Lyman series, so what are they looking for? The transition from 2 to 1. But if someone asks you what is the wavelength of the first line of Balmer series, then it is 3 to 2. If someone asks you what is the transition, what is the third line of Balmer series, the first line of Balmer is 3 to 2, the second line of Balmer is 4 to 2, the third line of Balmer is 5 to 2. Right? So that could be a way the question is framed. Right? Also, I want you to notice something. The first line of Lyman is 1216. Then the second line has emitting photon 1026, then 972, and then at series limit it is 912. What is happening to the wavelength of the photon emitted? It is decreasing. As the jump becomes bigger and bigger, the energy difference becomes bigger and bigger. So what is the energy of the photon emitted? Larger and larger. And what is energy of a photon? Energy of a photon is hc by lambda. जितना energy ज़्यादा होगा उस photon का wavelength उतना ही क्या होगा? कम. Right? So the larger the energy difference, the smaller will be the wavelength of the photon emitted. Yes or no? Right? That is why the first jump is 1216. And then as the energy difference keeps increasing, the wavelength of the photon emitted keeps decreasing. Yes or no? Right? Same thing over here. Right? So the lowest energy transition for Balmer series will be what? 3 to 2. But the highest energy transition for Balmer series will be what? Infinity to 2. If someone asks you what is the smallest wavelength of Balmer series, what is the smallest wavelength of Balmer series, what transition are you looking for? Infinity to 2. Because the smallest wavelength will correspond to the largest energy difference, which will be from infinity to 2. Are you getting it? Right? Calculate this. Electron is jumping from 4th orbit to 3rd orbit. 18,000 के आसपास कुछ आते हैं यार. हाँ? Now where does this photon lie? Infrared. If electrons jump from higher orbit to the 3rd orbit, then they lie in the infrared region. N1 equal to 3, and then they could jump from anywhere. right? The electron could jump from 4 or 5 or 6 up to infinity. This is known as the Bastian series, and this lies in the infrared region. This is known as the Bastian series after the scientist Bastian, who studied these lines. Lyman, Balmer, Bastian, these are all names of scientists, right? The electron could jump to the fourth orbit from a higher orbit. So the higher orbit could be 5, 6, 7 up to infinity. This is known as the bracket series. This is also infrared. The electron could jump to the fifth orbit from higher orbit like 6, 7, 8 up to infinity. This is known as the Fund series, PFUND. The Fund series. This is also infrared. Then the electron could jump to the sixth orbit from a higher orbit like 7, 8, 9 up to infinity. This is known as the Humphrey series. Also infrared. Are you getting it? Yes. So if the electron jumps to the first orbit, that is the Lyman series, to the second orbit, Balmer, third orbit, Bastian, fourth orbit, Brackett, fifth orbit, Fund, sixth orbit, Humphrey. Now you could get a question like this. Solve this please. Calculate the wavelength for the third line of Balmer series, of Bastian series, chalo, in helium plus atom. Please solve. Calculate the wavelength for the third line of Bastian series in helium plus atom. 9380. 8244. तुम्हारा कितना है? तीन अलग आंसर आ गए. चेक करते हैं. See what will be the wavelength emitted. It will be 912 upon Z square is the term which appears here. What atom is this? Helium plus. So what is Z for it? 2. So there will be a 2 square term appearing over here. And we want the third line of Bastian series. So what is the first line of Bastian? 4 to 3. Second line of Bastian, 5 to 3. Third line of Bastian, 6 to 3. So we want the transition from 6 to 3, right? So this will be 1 by 3 square minus 1 by 6 square. This many hours. होगा. मैं तो question अभी just बनाया. So are you getting it? Did you do this? हाँ? ऐसा कैसे हो सकता है? 2736. I want you to pay attention to this value as well. 2736 lies in which region? Ultraviolet. This is Bastian series, but where is the photon being emitted? In ultraviolet. Please note, ये जो मैं UV visible infrared लिखा हूँ, this is for hydrogen atom. This is which atom? Helium plus. Right? So Balmer series is in the visible range for hydrogen atom. It is not necessary that it will be in the visible range for helium plus also, for lithium plus 2 also. That's not necessary. It is in the visible for hydrogen. इसलिए ऊपर for hydrogen करके लिखा हुआ है. Are you getting this? Any doubts here? Please solve question 7. Please solve question 7B, 7B, and then 8. What is the second Lyman series in helium plus atom? 256.5. Good. What will be the minimum wavelength for Balmer series? Minimum wavelength will correspond to the largest transition from infinity to 2 because it's Balmer. And what will be the maximum wavelength for Balmer? In helium plus, from 3 to 2. Yes or no? Minimum wavelength will be from infinity to 2 and maximum wavelength will be from 3 to 2. Yes? Straightforward? Right. Take it. Now, one last thing regarding spectral lines. If I have a sample of gas in which the electrons are in an excited state and they jump back to the ground state, right? There are many atoms which I have, right? So not all electrons will jump back in the same way. They could follow different paths. Now my question is, in a sample of, let's say, hydrogen, electrons are in the third excited state, right? In a sample of hydrogen, the electrons are in the third excited state. How many unique how many unique spectral lines are possible? How many unique spectral lines are possible when they return to ground state? Tell me. In a sample of hydrogen, electrons are in the third excited state. How many unique spectral lines are possible when they return to ground state? 6 is correct. Good. Now, ध्यान दो. The electron is in third excited state, means the electron is here in n equal to 4. This is where the electron is. Now, one possible transition is that the electron jumps directly back, right? From 4 to 1, it jumps directly, which means it will release one particular kind of photon. Let me call it photon kind 1, right? Another possibility is that the electron could do this from 4 to 3, then 3 to 2, and then 2 to 1. This is possible. So it would release another photon of the type 2, 3, 4. These are all going to be different photons. Yes. Can you tell me any other photons which are possible? 4 to 4 to 2. Yes. 4 to 2, and then it can jump further from 2 to 1. So this will be photon number 5 in the jump from 4 to 2. And what about 2 to 1? It will not be 6. It will be the same as 4. Very important. If the electron jumps from 2 to 1, it does not matter वो उसके पहले कहाँ था. Any transition from 2 to 1 will release the same photon because the energy difference between 2 to 1 is fixed, right? So if the electron jumps from 4 to 2, that will release a new kind of photon. But then from 2 to 1, it is the same photon which we saw here, photon number 4. I will not count it twice. It's the same line. What is the question asking me for? How many unique spectral lines will be visible? Yes, it could jump from 4 to 3 and then it could jump from 3 to 1. Yes. But will I count this photon again? No, because that is photon number 2. I've already counted it. But then 3 to 1 is a new transition. That is photon number 6. Are there any more photons possible? Are there any more transitions possible? No. Right? ये अलग-अलग atom के लिए. Suppose question में था in a sample नहीं, in one atom of hydrogen, how many unique spectral lines are possible? Maximum 3. If I had one single atom, then what were the maximum number of lines possible? 3 na? 1, 2, 3. And what were the minimum number of lines? 1. But what is the question saying? I have a sample of hydrogen, means I have many atoms in which the electrons are in the third excited state, in which the electrons are in orbit number 4. So the total number of unique spectral lines are 6. Right. So we'll make a small table. Orbit number and number of unique spectral lines. If the electron is in the first orbit, how many unique spectral lines are possible? 0. 0. If it is in the first orbit, then वो और नीचे नहीं घुस सकता. It is in the ground state. It cannot emit photons at all. Right? The number of spectral lines are 0. If the electron is in the second orbit, how many spectral lines are possible? Just one. Those 2 से 1 एक ही possibility है, just one. If the orbit is 3, how many spectral lines are possible? 3. Right? What are those? Suppose electron third orbit में, तो क्या क्या कर सकता है? 3 से 1 directly आ सकता है, or it could go from 3 to 2 and then 2 to 1. So 1, 2, 3. 3 unique transitions, which means 3 unique photons I will get, 3 unique spectral lines I will get. This is 3. For 4 we saw 6. Yes, if the electron was in the fourth orbit, then we saw 6 lines. I will give you a formula for this. In general, if the electron is in the nth orbit, then the number of spectral lines you will get is n into n minus 1 by 2. Please remember this. If an electron is in orbit number n and it returns to the ground state, then the number of unique spectral lines which you can get is n into n minus 1 by 2. You can directly apply this formula, right? So if the electron is in the fifth orbit, how many unique spectral lines are possible? 10. Sixth orbit, 15, and so on, right? You can use this formula directly. So if the electron is, let's say, in the sixth orbit, then what are the unique transitions? You can actually draw it like this. From 6, it could jump directly to 1. This is possible. Then from 5 to 1 is possible. 4 to 1, 3 to 1, and 2 to 1. These are all the transitions which are possible for the electron when it jumps from any orbit to 1. Right? So essentially these are the 5 lines which I will get in the Lyman series. और तो कोई भी transition possible नहीं है ना 1 के ऊपर. Yes or no? Right? What Balmer series line will I get? 6 to 2, 5 to 2, 4 to 2, and 3 to 2. I'll get 4 lines in the Balmer series. Then I'll get I'll get 3 lines in the Paschen series. I'll get 2 lines in the bracket series, and then I'll get 1 line in the fund series. Lyman Balmer Paschen bracket fund. Yes? Are you getting it or not? Right? How many total lines do we see? 15. If the electron is in the 6th orbit, then the different ways in which it can lose energy and come back to the ground state, we will get 15 unique lines on our spectrum. Any doubts? Cool? Right. We'll stop here today. In the next class, we'll start with class assignment 3. And your homework now is section B and section C. Not much homework. Section B has 28 problems, which are on the ionization energy and these things which we learned today. Section C is on spectrum and spectral lines, which we studied today as well. Section D is de Broglie's and Heisenberg's, which we will start in the next class.
First thing is this: if I have an atom, सबसे पहले तो energy का बात करते हैं, ठीक है? Whenever we are measuring energy, we always need a reference point, right? I'm sure all of you know this, that suppose I have a ball, right, and it is on the surface of the earth, okay? This is our reference point when it comes to a gravitational field. When we are doing mechanics the problems, what do you say is the potential energy of this ball? Zero. Potential energy is 0, right? And now if I take this ball up a certain height, right, if I take this ball to a height h, sorry, if I take it to a height h, and then if I ask you potential energy,
mgh
potential energy is mgh. ये तुम लोग सबको पता है. Now tell me this: suppose मैं इस बॉल को एक गड्ढे में ले जाऊं, right, and let's say this pit is of depth h. Can you tell me what will be the potential energy of the ball here?
zero
No. If this is our reference point, then the potential
minus mgh
minus mgh.
yes
Right? This potential energy is going to be minus mgh, because what is our reference point? Zero potential कहाँ पे है? यहाँ पे zero potential है, right? अगर यहाँ potential energy नहीं है, तो अगर मैं बॉल को यहाँ से रिलीज कर देता हूँ, if I release the ball from here, will it not fall down? Right? ऐसा तो नहीं है कि यहाँ फ्लोट करता रहेगा, right? ये तो नीचे गिरेगा ना, मतलब इसके पास कुछ पोटेंशियल एनर्जी तो था, तो इस पॉइंट पे पोटेंशियल एनर्जी कितना होगा? उससे कम होगा, right? Because when an object falls, it loses potential energy. But if we started with zero, then what will the potential energy at this depth become? Negative, right? So the idea is that whenever we are measuring potential energy, we always take a reference point कि भाई यहाँ पे potential energy zero है. Now from this point, if I lose energy, then my potential energy will decrease, and if I gain energy, my potential energy will increase. Like for example, if my ball is here right now, it is on the surface of the earth, its potential energy is 0. If I do work on the ball, where am I moving it? I'm moving it in which direction? Batao. Please अपने आप को mute करो unless you're not responding. If I'm moving it in the upward direction, in which direction is the force? Gravitational force किधर है?
downward
Right? Gravity is downwards.
down
Okay. So since I'm moving it against the force, what will happen? Its potential energy will increase. So from 0, it becomes mgh. But when I'm moving it downwards, in which direction am I moving it? I'm moving it in the direction of the force.
down yes sir
Yes. So
yes,
what will
sir.
happen to potential energy? It will become negative. right? So in case of an atom, what do? This is the nucleus, and this is the electron. Okay. In which direction is the force? Electrostatic force is in which direction?
Towards nucleus.
Towards nucleus. Electrostatic force is in this direction, towards the nucleus, right? Now, if I start moving my electron towards the nucleus, what will happen to potential energy?
Decrease.
Potential energy will decrease. Now, when it comes to atoms, हम लोग 0 point किसको choose कर रहे हैं? Infinity, right? Infinity is our reference point. And this potential energy at infinity is 0. That's the whole idea. हम लोग जब एक ग्रेविटेशनल फोर्स फील्ड में है तो हम लोग अर्थ का सरफेस को रेफरेंस पॉइंट मान लेते हैं एंड बोलते हैं कि भाई यहाँ पे पोटेंशियल एनर्जी 0 है. बट व्हेन वी आर टॉकिंग अबाउट एन एटम, वी से दैट एट इनफाइनाइट डिस्टेंस फ्रॉम द न्यूक्लियस द पोटेंशियल एनर्जी इज 0. That is our reference point. Now from that reference point, if I am moving towards the nucleus, in which direction am I moving? I'm moving towards the nucleus. I'm moving in the direction of the force. So what will happen to the potential energy? It will become negative. Which is why whenever we calculate the energy, the potential energy of an electron, what does it come to? It is a negative value. Are you understanding? Just like this ball has
once more please.
Whenever we move in the direction of the force, यहाँ electrostatic force left के direction में है, and हम electron को move भी कहाँ करा रहे हैं? Left के direction में, right? So whenever we move in the direction of the force, the potential energy decreases. And whenever we move opposite to the direction of the force, the potential energy increases. तो अगर reference point infinity है and वहाँ पे potential energy 0 है, तो अगर मैं force की direction में अब nucleus की तरफ move करूँगा, तो potential energy क्या होगा? Decrease होगा. 0 से decrease होगा तो ये value क्या होता जाएगा? Negative. Okay. Now let's move on. I want to give you some other some feel about energy levels. If you look at the formula for energy, the formula for energy is minus 13.6 into z square by n square. Okay. So if you see the first orbit, let's take the hydrogen atom for simplicity's sake. Okay. If I have the hydrogen atom, then z is 1. Okay. So what is the only variable as I keep moving to higher and higher orbits? The only variable is n. Right? Now, if I have n equal to 1, ये energy कितना है? Let's write down the energies. N equal to 1, n equal to 2, n equal to 3. Right? The energy over here is minus 13.6. Okay, electron volts. The energy of the second orbit, if you look carefully, is minus 13.6 upon 2 square. Okay. The energy of the third orbit is how much? Minus 13.6 upon 3 square. Upon 9 ho jayega, right? So in general, if I keep moving to higher and higher orbits, okay, I can have a general formula for the energy of the electron in that orbit. If I am at orbit n, then the energy of the electron at orbit n is going to be minus 13.6 upon n square.
Yes, sir.
Okay, it's going to be minus 13.6 by n square. So that is what many questions have been based on. Ki instead of giving you minus 13.6, there are some questions which tell you ki chalo jo electron first orbit mein, it has some minus 50 arbitrary units. Right? This is the energy of the electron in the first orbit, minus 50. Then how much will be the energy in the second orbit? Minus 50 by 2 square. Right? First orbit में electron का energy जितना भी होगा, second orbit में उसका 1/4 होगा, third orbit में उसका 1/9 होगा, fourth orbit में उसका 1/16 होगा, and ये इस order को follow करेगा ही हमेशा. Right? So this could be any value. You can always compare it to the energy of the first orbit. Are you getting it? Another thing which I wanted you guys to appreciate and feel, look at the formula of radius. Okay. Radius is 0.529
n square by z
into n square by z.
N square by
z
z.
square nahi hai. It is n square by z, and this will give you the radius in Armstrongs, right? And let's take for simplicity the hydrogen atom, right? Let's say ये nucleus है, this is orbit 1. Okay, so can you tell me how much is the radius of the first orbit? 0.529.
Yes, sir.
Right, this distance is 0.529 Armstrongs. Now let's say this value is some a naught. Okay, let's say this value is a naught. Now if my atom is the same, that means z is fixed. Okay, so what will be the radius of the second orbit?
4 in it.
Radius of the second orbit will be, yes, 0.529 into 2 square by z is same, right? So this is effectively what? 4a naught. तो समझो ये a naught था, तो अगला ऑर्बिट यहाँ है, right? And this distance, sorry, this distance is 4a naught.
2.116 Armstrong.
Yes, how much ever that is not the point here. This distance is 4a naught. Then where will the third orbit be?
9 in it. 9 in it.
9a naught.
तो वो इधर कहीं आएगा,
9 and not.
right? That will be somewhere here. So ये ऐसे अगर measure करूँ, this is going to be 9a naught, right? So appreciate that the orbits are not equidistant. ठीक है? What is the difference in distance between the first and second orbits? इनके बीच में difference कितना है?
3 in it.
3a naught. But फिर second और third के बीच में distance कितना
5 in
है?
it.
5 and not.
5a naught, right? That's what I wanted you to understand, that it is not that the orbits are equally spaced. ये फिक्स डिस्टेंस पे नहीं है, पहला ऑर्बिट फिर दूसरे ऑर्बिट और ज्यादा, तीसरा उससे भी ज्यादा, चौथा उससे भी ज्यादा, मतलब द डिफरेंस, द डिस्टेंस बिटवीन द ऑर्बिट्स इज आल्सो इंक्रीजिंग.
सर एपी में इंक्रीज कर 3 5 6 7
Yes,
ऐसे इंक्रीज
yes,
कर रहे हैं.
that is an AP. Anyway, so do you feel what is happening here? You know, many times while solving problems, while drawing diagrams, I draw all the orbits equally spaced, n equal to 1, n equal to 2, n equal to 3, n equal to 4, but that is not really the case, right? That's what I wanted to emphasize by showing you this, कि जो distances है वो increase कर रहा है. 1 और 2 के बीच में distance जितना था, 2 और 3 के बीच में उससे ज्यादा है, 3 और 4 के बीच में उससे भी ज्यादा है, right? That is what you have to appreciate here, that the distances between the orbits is increasing. Cool. Again, taking the hydrogen atom as reference, another thing which I wanted to emphasize here, 13.6 minus 13.6 electron volts, this is the energy of the first orbit. Second orbit, third orbit here. Writing the energies, minus 3.4 electron volt, minus 1.51 electron volt. Now, if you notice the difference in energy, okay, ध्यान दो, how much is the difference in energy between these two?
10.2.
10.2 electron volt, right? But the difference in energy between 2 and 3 is not 10.2.
Yes sir.
Okay, this is
1.9.
1.89 electron volts, right? So, and then if I look at between 3 and 4, what will that be? Even lesser, right? If I see n equal to 4, then this difference is going to be even lesser. So the idea is that between orbits, the difference is also decreasing. Okay? As we keep moving higher and higher into the atom, the difference in energy between the orbits is also decreasing. इसीलिए हम क्या देखते हैं, that when an electron falls to the first orbit, the high energy photons are emitted, you know, ultraviolet are emitted. But when here electrons are falling, what do I get? I get visible, right? The energy difference has decreased, right? If there is a fall over here, what do I get? Infrared, because the energy difference has again decreased. So as I keep moving to higher and higher orbits, the difference in energy between the orbits is also decreasing. Let's understand. Say I give you this. In a container, there is one atom of hydrogen in its third excited state. ठीक है, calculate maximum and minimum number of spectral lines that can be obtained. Please solve.
So 3 and 1.
4 and 1.
3 and 1, sir.
3 and 1.
Yes.
Minimum will be from 4 to 1. 4 to 1 and the maximum will be 4 to 3, 3 to 2, 2 to 1.
Oh,
Yes.
sorry, sir. 3 2. 3 and 1.
Correct. ठीक है. The electron is in the third excited state, means it is in the fourth orbit, right? And the interesting part of this question is that we have only one atom. We have single atom. हम लोग ये वाला formula कब लगाते हैं? N into n minus 1 by 2. This formula is used when we have a sample of gas. When we have many gas molecules or many gas atoms, then we will consider all possible transitions, because some atom will jump directly, some atom will jump half, some atom will do 2 steps, some atom will do 3 steps ground state. So all possibilities you have to count. Then we use this formula. This will give you all possibilities. Okay? But if the question has said only one atom is there, then maximum lines are what? Maximum lines is if the electron makes single jump. So one jump here, one jump here, one jump here, right? So max lines is 3. And minimum kab hota? Agar electron direct 4 से 1 jump kar leta, that would have been the minimum. So minimum line is 1. Is this okay? Does everyone get this?
Yes, sir.
Yes, sir.
Okay.
Sir, फिर तो सर कोई भी एटम अगर सपोज कोई भी एक्साइटेड स्टेट में अगर उसका मिनिमम निकालना है स्पेक्ट्रल लाइंस तो वो 1 ही होगा.
हाँ 1 ही
Correct.
होगा. हाँ
ठीक.
ठीक है, ये सबको क्लियर है?
सर तो बोर बोला था कि जब वो जंप कर रहा होगा तो वो बीच में रह सकता है कि नहीं रह सकता है वो?
यार वो 1 सेकंड के लिए रहता है. इट्स लाइक थ्रोइंग अ बॉल अप. ठीक है, तुम एक बॉल को ऊपर फेंकते हो तो वो अपना हाईएस्ट डिस्टेंस पहुंच के वापस नीचे आता है ना, वो उधर फ्लोट तो नहीं करता रहता. तो इलेक्ट्रॉन के साथ भी वही है. तुम इलेक्ट्रॉन को ऊपर फेंकते हो हायर ऑर्बिट में, वो एक बार जाता है फिर वापस नीचे आ जाता है. लाइक थ्रोइंग अ बॉल अप इन द एयर. दैट्स ऑल. ओके, नाउ आई एम गोइंग टू चेंज दिस क्वेश्चन. ठीक है, एंड टेल मी दिस नाउ. व्हाट इफ आई हैड गिवन यू 2 atoms? Solve again. In a container there are 2 atoms of hydrogen and they are in the third excited state, let's say, and I ask you the same question again. Find out the maximum and minimum number of lines.
So I think
4 and 1. 4 and 1. Yeah.
4 and 1.
Yeah, 4
I
and
would
1.
Okay, let's understand. I have 2 atoms now. I have 2 atoms, right? The minimum number of lines will be when electrons in both of these atoms jump directly. ठीक है, यहाँ का भी इलेक्ट्रॉन डायरेक्ट जंप मारा एंड इसका भी इलेक्ट्रॉन डायरेक्ट जंप मारा, here to here, right? And the interesting thing is that the photon emitted here and the photon emitted here will be the same, because it is the same transition of the same atom. So the photon from 4 to 1 in both the atoms will be same. So how many lines will we see? Just 1, right? So the minimum number of lines is 1, right? Now for maximum I'll try to do what? Let's say इसमें तो इस atom में जो पहला atom है उसमें कितने lines मिलेंगे? 3, right? उसमें I can get 3. Now in the second atom how many lines will you get?
2. Either 4 to 2 or 4 to 1 directly.
You could do this 4 to 2, right? You could do this, but then this 2 to 1 you've already counted over here,
Yes.
right? So this line and this line will be same. So how many new lines can you get over here? Just 1. You can get only 1 new line. So the max is going to be 4. ठीक है? This is a good question. Let's see if you can solve. Okay. A container has a sample of hydrogen, helium plus, and lithium plus 2 gas with electrons in the 5th excited state. All electrons return to ground state. Calculate the max number of spectral lines. Yeah, total calculate the total number of spectral lines which can be obtained. Please solve. A container has a sample of hydrogen, helium plus and lithium plus 2 gases. एक container में 3 अलग-अलग type के atom में भर दिया हूँ with electrons in the 5th excited state. हर एक atom में electron 5th excited state में है. All the electrons are returning to ground state. Calculate the total number of spectral lines which can
Sir,
be.
all possibilities.
Yes.
You have to. It's 45.
नहीं wrong.
So because everything.
अरे
will
बाबा
have
हम
to be-
wrong बोला ना. अब सोचो थोड़ा सा. 45 is the obvious answer जो सबके दिमाग में एक बार में आएगा, but इसमें क्या गलत हो रहा है ये सोचो. Okay, I want all of you to pay attention here. This is a very interesting concept. In the hydrogen atom, ठीक है, there is a transition which is taking place, right? Let's say from N2 to N1, right? And this transition releases a particular photon of wavelength lambda, right? Now, the same transition in lithium, or let me talk about helium first. The same transition in helium plus will not release the same photon. ये तो अपने को पता ही है, because lambda का formula क्या होता है? Lambda is 912 upon
Z square.
Z
By-
square 1 by N1 square minus 1 by N2 square. Right? This is the formula. So if Z changes, then the lambda will change. That we are sure of, right? So if I do the same transition in helium plus, the Z will be different, so the lambda will be different. But what I'm trying to say here is, let's take a particular transition as example and work with that. Okay? Say the electron is moving from 2 to 1, right? Say this is the transition which is happening. I want to find out some other transition in helium plus which will emit the same photon which was emitted in the transition 2 to 1 in hydrogen. Okay, please understand carefully what I'm saying here. Hydrogen में 2 से 1 में जो photon emit हो रहा है, helium plus में कोई दूसरे transition के लिए ये same photon emit हो सकता है, right? And that I need to find out what it is, right? So let's say in helium plus it is N2 to N1. Okay, in helium plus let's say it is N2 to N1, and यहाँ पे let me put the formula for hydrogen over here. If I put it 1 by 1 square minus 1 by 2 square, right? Let's say I have this over here. Now in helium plus, the wavelength will be 912 upon Z के बदले 2 लगाना होगा, 2 square 1 by N1 square minus 1 by N2 square. And in case of hydrogen, this Z is how much? This Z is 1. Okay, this is 1 square, right? Now, if these two wavelengths have to be the same, I will do a small modification here. Pay attention. I will take this 2 square inside the bracket. And in the denominator. So this expression on the right, I can write as 912 upon 1 bahar reh gaya, 1 by N1 by 2 whole square minus 1 upon N2 by 2 whole square. Tell me if this is clear.
Yes, sir.
This 2 square I have taken inside the brackets and I have brought it in the denominator with N1. So I can bring this 2 inside and this will become 1 by N1 by 2 whole square minus 1 by N2 by 2 whole square. Now, if these two wavelengths have to be the same, then this value and this value must be same, and this value and this value must be same, meaning N1 by 2 is equal to 1, which means N1 equal to 2, and N2 by 2 is equal to 2, which means N2 is equal to 4. Right? ये जो 2 square है, this 2 square over here, it goes into the numerator and then you can take it out of the bracket, so it will come as 2 square over here. Right? So what is clear from here? That hydrogen atom में 2 से 1 में जो photon निकलता है, वो same photon helium plus में 4 से 2 transition में निकलता है. Okay, that same photon is emitted in helium plus when the transition is from 4 to 2. And if I were to consider lithium over here, then what transition in lithium would give me the same photon? if I had lithium plus 2 over here, then over here this would be 3 square.
328.
This would be 3 square, and then this would be n1 by 3 and n2 by 3. So the transition would be what?
6 to 1.
6 to 3.
Yes, sir.
6 to 3 would give me the same photon which is emitted in 4 to 2 in helium plus, which is emitted in 2 to 1 of hydrogen. Okay, so I will generalize this result now. I will generalize this result. In general, if hydrogen atom has a transition from N2 to N1, then the same photon will be released in helium plus when the transition is from 2N2 to 2N1. And the same photon will be released in lithium plus 2 when the transition is from 3N2 to 3N1, and so on. Okay? These are going to release the same photon. Same photon is emitted in these transitions. Okay, so what can we say then? Fifth excited state means electron was where? In the sixth orbit. So hydrogen के लिए कौन-कौन सा line मिलेगा अपने को? We will get 15 lines for hydrogen. We'll get 15 lines for helium plus, and we will get 15 lines for lithium plus 2. Right? Give me 2 minutes. I'll just draw it. I'll send you the image. Don't worry about it. These are the 15 lines of hydrogen. You can notice there are 5 lines in the Lyman series, 4 lines in the Balmer series, 3 lines in Paschen, and then 2 lines in Brackett, and 1 line in Fund. Right. So all of you saw these 45 lines. Okay, these were the 45 lines which most of you counted, which is correct, but there are some lines which have been repeated. 15 lines from each, but some lines have been repeated. Kaun sa? Can you tell me which photons are the same? Let's take, for example, this 2 to 1 in hydrogen. I have already counted. Okay, can you tell me which transition in helium plus will release the same photon?
4 to 2.
4 to 2.
4 to 2.
4 to 2.
4 to 2. तो इसको हटाना पड़ेगा ना, क्योंकि ये सेम फोटोन है, उसको एक बार काउंट कर चुके हैं, so -1. ठीक है, which transition in lithium plus 2 will release the same photon?
6 to 3.
6 to 3.
6 to 3.
6 to 3. So I will have to remove this as well. -1. ठीक है, can you tell me what other photons have been counted twice?
So 6 to 2 in helium plus. From like 3 to 1 का transition में 6 to 2 का same है.
Correct. Very good. 1 second. I'll use another color. 3 to 1 in hydrogen will have the same photon which is emitted in 6 to 2 in helium plus. So this has also been counted twice.
तो 6 to 4 भी cancel हो
6 to 4 भी.
तो ये भी -1
होगा.
हो गया. Yes. Good. 3 to 2 of hydrogen. अच्छा ध्यान देना. 3 to 1 of hydrogen, 6 to 2 of helium plus I have counted again. What transition in lithium plus would this be?
No transition.
9 to 3.
9 to 3.
But I have not counted that only, so that's okay. And 3 to 2 in hydrogen will have what in helium plus?
6 to 4.
6 to 4. So I will have to remove this also. -1. Okay. And what transition in lithium plus 2 corresponding?
No transition.
It would be 9 to 6.
9 to
9 to
6.
6, but I have not counted that. Right? So I have removed all photons which I counted more than once. So the answer is 41. And I'm going to discuss a question now जो तुम्हारा स्कूल एग्जाम में फर्स्ट टर्म में आएगा ही आएगा. ठीक है, ये हर स्कूल टीचर का फेवरेट क्वेश्चन होता है. So I'll discuss that question as well. ठीक है. One formula which I did not give you is this. I gave you the formula for the radius in a hydrogen species, right? Inside this, we have the nucleus, right? The nucleus we understand is a very, very tiny point in the atom. We have a formula for radius of nucleus also. Please, ये important है, इसको लिख लो. The radius of the nucleus is approximately, ये exact नहीं है, but it is approximately 1.2 into 10 to the power minus 15 into a to the power 1 by 3 meters. Please remember this. Proof that the density of any nucleus, by any nucleus I mean कोई भी atom का nucleus ले ले, is same. Okay, you will get this question in your unit test or school exam, I'm sure of it. Okay, the question is this: prove that the density of any nucleus is same. Okay, so let's take any nucleus. The atom is X, its mass number is A, and its atomic number is Z. Okay, now if I have any nucleus, what is the formula for density? Density is mass upon volume.
Volume.
Right? Now, if the mass is, let's say, mass number is A AMUs, right? अगर mass number A है, तो what is the mass of one single atom? A AMUs, nucleus के अंदर weight कितना होगा? A AMUs. So if I convert it into kg, what will it become? This will be A into 1.66 into 10 to the power minus 27 kg. है कि नहीं? This is the weight inside the nucleus, right? Upon what? Divide क्या करेंगे? Volume से. Now, what will be the volume of a sphere? What is the formula?
4 by 3 pi r cube.
Sir,
4 by 3 pi.
Yes. So this will be 4 by 3 into pi into. Now radius we know is how much? 1.2 into 10 power minus 15 into a to the power 1 by 3 का cube. बोलो.
So we will get cancelled.
Yes. So what will happen is the a term will get cancelled. ये a और ये a cancel हो जाएगा. Okay. Let's not cut the 3 away. This a and a will get cancelled. So can you tell me how much is this value coming to? Please solve. It will come to 2.3 into 10 to the power 17 kg per meter cube. ठीक है. Now I want you to look at this value and imagine this value. ठीक है. This is the density of the nucleus and ये हर nucleus के लिए same है. Every nucleus in the world, right, has the same density, which is this much, 2.3 into 10 power 17 kgs per meter cube. Now feel this. ठीक है. थोड़ा सा सोचो यार, 1 मीटर क्यूब कितना होता है? How much is 1 meter cube? Right? 1 meter, this much, right? 1 meter height and 1 meter breadth, right? Length, breadth, height, 1 meter. So 1 meter cube is smaller than your room. It's a volume which is much smaller than the room you're sitting in, right? Do you understand 1 meter cube? That's nothing, right? And look at the amount of mass which is there in 1 meter cube. 2.3 into 10 power 17 kgs. Can you think this is like millions and millions of kilograms fitted in how much space? In 1 meter cube. So what we understand from here is that the nucleus of an atom is incredibly dense. The nucleus of an atom is incredibly dense. Can you feel this density? ये कितना ज़्यादा density है तुम feel कर सकते हो. Let's say I wanted to find out the volume which our Earth would occupy. ठीक है? If it was this dense, अगर अपना Earth का density इतना होता, तो Earth का volume कितना होता? ये मैं निकालना चाहता हूँ अगर. ठीक है? So do you know the mass of the Earth? The mass of the Earth is 6 into 10 to the power 24 kg. ठीक है? This is the mass of the Earth. Can you find out the volume? Can you find out the volume? Volume is what? Mass by density?
4 by 3 pi r cube.
Mass by density. Suppose Earth इतना dense होता. This is what we call nuclear density, right? Suppose our Earth was as dense as the nucleus of an atom, right? If this was true, then what would be the volume of the Earth? Can you find this out? 6 into 10 power 24 upon density 2.3 into 10 power 17. ये kg में है.
10 to the power 7.
This is
Sir,
kg
approximately 3.
per meter cube. तो ये अगर मैं solve करूँ,
2.6 into 10 to the power 7.
Sir, approximately 3 into 10 to the power 7 meter cube. Less than 3 into 10 to the power 7 meter cube.
this will come to 2.6 into
2.6 into 10 to the power 7.
into 10 power 7 meter cube, right? Now you might feel कि अरे ये तो बहुत बड़ा volume है, but imagine this is meter cube, huh? This is meter cube. So if you were to compress this in a sphere, let's say, इसको अगर तुम circle में बनाते, let's say I say this volume is 4/3 pi r cube. Can you find out this radius? This will come to 184 meters. What I wanted to explain through this is, ध्यान से समझो, I found out the density of the nucleus of an atom, and this density came out to be 2.3 into 10 power 17 kg per meter cube. Please remember, prove that the density of any nucleus is same. You will get this question in your school exams. And this value, the density is this much. Now I'm thinking, what if the Earth was made up with the same density? What if we wanted to fit the Earth in a space so that this would be the density? Okay? I calculate the volume of this space which is required, and if that space is a sphere, then it has radius 184 meter only. Can you imagine 184 meter? 184 meter is what? It is maybe तुम्हारे घर से closest bus stop.
Nearly the size of Statue of Unity.
हाँ ठीक है, Statue of Unity समझ लो, ठीक है, 184 meter. Now imagine that you have a sphere. Imagine you have a sphere of radius 184 meters, right? The size of Statue of Unity उतना बड़ा एक sphere है, right? The density of the nucleus is so large that the entire Earth could fit inside that sphere, right? Our entire Earth can fit inside a sphere of radius 184 meters. Then that density would be equal to the density of the nucleus of any atom. Okay? That is the idea which I want to put across to you. I really want you guys to feel that the density of the nucleus is very, very large. बहुत large होता है. And this is a homework for you. If you want, you can read about neutron stars. Have you heard about this term? Maybe in some sci-fi.
No, sir.
No, sir.
No, sir.
Okay. Neutron stars are basically stars which are made up of nuclear material.